Imagine you're trying to divide a massive, just scrawling network into two distinct groups. This could be, a city's power grid, a complex social network.
Or, well, even the microscopic wiring inside the device you're listening to right now.
Yeah, exactly. But your goal here isn't to just isolate these two groups. Your goal is to actually maximize the connections that cross that dividing line.
Which, I mean, it sounds totally counterintuitive. Usually, when we fracture a system, we want a clean break,
Right.
like minimal entanglement.
But think of it like hosting a massive dinner party. You have to split your friends into two separate tables because of space, but you want the party to be lively, right?
Yeah.
Chaotic, even.
Oh, I see where you're going with this.
Yeah, so you want to maximize the number of close friends sitting at opposite tables. You're forcing them to like shout across the room and mingle between the two groups. You want the highest possible weight of connections crossing the gap.
That is, wow. That's a brilliant way to visualize the core tension of the Mancus key problem. I love that. It's really the mathematical art of finding the optimal fracture point in a system, just to maximize the tension across that fracture.
And that tension is basically the central mission for our deep dive today. We are exploring a super fascinating 2026 presentation by a researcher named Luck036. It's titled Hadlock's Algorithm for Planar Maxicity and MWPM Optimization.
Quite a mouthful.
It is, yeah. But we're going to unpack this brilliant mathematical breakthrough from 1975 that took a famously impossible problem and found a cheat code to solve it. And then we'll get into a modern optimization that takes this 1975 logic and makes it run at like absolute lightning speed.
Well, to really appreciate the elegance of this cheat code, we first kind of need to understand the nightmare that this problem presents in the wild.
The impossible part.
Exactly. If you have a general graph, just a random messy web of nodes and connections with no specific structure, Mexity is basically unsolvable in a reasonable time frame. It falls into a category computer scientists call NP-hard.
Right, and let's translate that for a second. NP-hard basically means the complexity scales so aggressively that as you add more nodes to your network, the number of possible ways to split the group just explodes factorially.
Oh, it's brutal.
If you tried to brute force a solution for a network of any real size, I mean, even a supercomputer would be crunching numbers until the heat death of the universe.
Yeah, literally. For decades, handing a mathematician a general graph and asking for the absolute maximum cut was, well, a guaranteed way to get laughed out of the room.
Right, because you just couldn't do it.
You couldn't. Historically, the best we could do was rely on incredibly heavy geometry to find approximations. The famous one is the Goldman-Williamson SDP algorithm.
Okay, but that's just a guess, right?
Yeah, exactly. You don't get the perfect optimal answer. You just get a mathematically good enough guess. I mean, the only time it was easy was if your graph happened to be perfectly bipartite.
Meaning it naturally splits into two neat groups already.
Right, where all connections already cross the divide. In that rare case, the problem is trivial. You literally just cut down the middle.
But the real world is messy. Most networks aren't perfectly bipartite. Which brings us to the specific arena where Hadlock's 1975 algorithm operates, which is planar graphs.
Yes, this is where the impossible suddenly becomes possible.
So let's define that. A planar graph is a network with a very strict geometric rule. You must be able to draw it on a flat piece of paper or the surface of a sphere without any of the connecting lines, the edges crossing over each other.
Like a map with no overpasses. Every single intersection has to be an actual node, a physical location in the network.
And mathematics is pretty ruthless about enforcing this.
Oh, absolutely ruthless. To be considered planar, a graph strictly excludes certain inherent structures. For instance, if your network contains a fully connected group of 5 nodes, what mathematicians call K5, it's game over.
Because you can't draw it.
Right. There is simply no physical way to draw 5 nodes, all connected to each other on a flat plane, without at least 2 lines crossing. It also excludes a structure called a complete bipartite 3x3 graph, or K33.
So if either of those shapes is hiding inside your sprawling network?
It's not planar.
Yeah.
But if your network passes that test, a really fascinating geometric property emerges. The drawing of the network divides the blank paper into distinct enclosed regions. We call these empty spaces faces.
Okay, wait. I have to push back on this definition of faces because looking through the source material, something felt like a total mathematical cheat to me.
Oh, how so?
Well, I totally understand faces when they are enclosed, right? Like if I draw a triangle on a piece of paper, the empty space inside that triangle is a face. It's clearly bounded by the 3 lines.
Right, makes sense.
But the math dictates that the empty space outside the triangle, the blank paper stretching out to infinity in every direction, is technically considered a single face with a boundary. I mean, how can infinity be a bounded region?
Yeah. It does feel like a cheat when you restrict your mind to a flat, two-dimensional piece of paper. But remember the full definition we just talked about.
The sphere thing.
Exactly. A planar graph can be drawn on a plane or the surface of a sphere. So imagine taking that flat piece of paper with your triangle drawn on it and wrapping it perfectly around a globe.
Oh, wow. Okay, I see it now.
Right. The infinite outer space wraps around the back of the sphere and closes in on itself. On a spherical surface, the so-called outer face is just another bounded region on the globe. It's completely democratized.
That is wild.
Yeah, mathematically, it's identical to the space inside the triangle. Infinity just disappears.
Wrapping it around a sphere democratizes the faces. The inside and the outside are just two different patches on a ball. I really love that perspective shift.
It's beautiful, isn't it?
So, okay, we have our planar graph, and we know it's composed of these faces, these empty spaces. How did Hadlock look at empty space and somehow use it to solve an NP-hard problem?
Well, he shifted his entire focus from the nodes to the boundaries. He categorized every single face in the network into one of two camps, even or odd,
And this is based on what?
based purely on the number of edges that form the boundary of that specific face. So a square is bounded by 4 edges, making it an even face. A triangle is bounded by 3, making it an odd face.
And this seemingly simple distinction, I mean, this is where the entire MaxUT problem breaks wide open, right?
It really does.
Because our goal is to divide all the nodes into two sets. Let's call them set A and set B. If a face has an even number of edges on its boundary, like a square, you can perfectly alternate the nodes as you walk around the perimeter. Set A, set B, set A, set B.
Exactly. Every single edge around that square will successfully cross from A to B.
Right. You can perfectly two-color it, every edge is included in your cut, and the face is completely satisfied.
But try applying that exact same alternating logic to an odd face, like a triangle.
You just can't. Node 1 is set A, node 2 is set B, node 3 goes back to set A, but now node 3 and node 1 are right next to each other, and they're both in set A.
Yep. The edge between them does not cross the divide.
It's trapped entirely inside set A. Mathematically, it is literally impossible to perfectly two-color an odd face. At least one edge on its boundary has to be excluded from your cut.
So odd faces are fundamentally frustrated. And that's actually the term used in physics and graph theory to describe this state. Frustrated. There's no perfect resolution for them. Someone is always left out.
It's like a three-person love triangle. Two people can pair off perfectly, but someone is always left out in the cold.
That's a perfect analogy. And there's this beautiful ironclad rule in planar graph theory called the handshaking lemma. It proves that every planar graph, no matter how complex, will always contain an even number of these frustrated odd faces.
So they always exist in pairs.
Always.
If you're listening to this and wondering why chip manufacturers or data scientists care about frustrated odd faces, this is the light bulb moment right here.
Oh, for sure.
If the even faces are perfectly happy and easily divided, and the odd faces are the sole source of the frustration, then finding the maximum cut isn't about looking at millions of individual nodes anymore.
Not at all.
It just becomes a highly targeted game of dealing with the odd faces.
Exactly. Hadlock realized that to solve MaxQT on a planar graph, you just need to identify these frustrated odd faces
Right.
and calculate the absolute cheapest way to pair them up and resolve their frustration.
Let's walk through how the algorithm actually does this step by step, because it's a really fascinating sequence of logical leaps. The first thing the computer does is verify the graph is actually planar, right?
Right. Using a standard library tool like Python's nx.checkplanarity. This maps out the embedding, so it gives the computer the exact geometric layout of the boundaries.
But the next move is where the genius really lies. The algorithm constructs what is called a dual graph.
Yeah, the dual graph is a complete inversion of perspective. You take every face from your original graph, the empty spaces themselves, and you turn them into the new vertices. And the new edges that connect these faces are the physical boundaries they share in the original graph. And if two faces happen to share multiple boundaries, the algorithm is smart enough to only keep the one with the lowest weight.
It's kind of like looking at a map of countries. In the original graph, the cities are the nodes, and the highways between them are the edges.
Okay, I like that.
But in the dual graph, the countries themselves become the nodes, and the physical borders between them become the connecting edges. The weight of that border is just the weight of the highway crossing it.
That is spot on. Once you have that map of countries, you filter it down. You basically isolate the troublemakers by stripping away all the even faces leaving only the odd ones.
The frustrated ones.
Right. Then the algorithm calculates the all pairs shortest paths. It explores the dual graph to find the absolute cheapest route across the borders to connect any odd face to any other odd face.
And because the handshaking lemma guarantees there's an even number of them, we know they can all eventually be paired off.
Exactly. Which leads us to a process called minimum weight perfect matching, or MWPM.
Right.
We take this matrix of shortest paths and calculate the optimal way to pair up every single odd face so that the total distance, the combined weight of all the paths, is as tiny as mathematically possible.
So we are finding the lowest possible cost to resolve all the frustration in the whole network.
Yes. Then comes the final crucial maneuver. We trace those optimal shortest paths in the dual graph back to the original highways, the primal edges in our network, and the edges that make up those paths are explicitly removed.
They're the edges we exclude from our cut.
You got it. The remaining edges form a bipartite subgraph, which is our MXCUT.
I just want to pause and highlight the sheer irony of this logic for a second. We are running this deeply complex, highly sophisticated algorithm to find the absolute minimum total weight.
Purely so we can throw it away.
Exactly. We are systematically hunting for the cheapest trash to take out. Because mathematically, throwing away the minimum guarantees that the pile of connections we are left holding is the absolute maximum.
It is a stunning bit of reverse engineering. Let's ground this with a simple triangle example from the presentation. It's a network with just 3 nodes and 3 edges. And let's say the edges have weights of 5, 10, and 3.
Okay, a triangle. That means it has 2 faces. The inner face, bounded by the 3 edges.
Right.
And the outer face, the rest of the world, which we now know wraps around our imaginary sphere, and is also bounded by those same 3 edges. So both faces are odd.
Both are odd. Both are frustrated. To pair them up and resolve the frustration, you have to cross from the inside to the outside.
Which means crossing one of the edges.
Right. You can pay a cost of 5, cost of 10, or a cost of 3. The shortest path algorithm immediately identifies the edge weighing 3.
So we exclude the 3, we literally throw it in the trash, and we are left with the edges weighing 5 and 10. 5 plus 10 is 15. That's our maximum cut.
You've just executed Hadlock's algorithm in your head. It is mathematically foolproof.
Which is amazing. But, if this logic was perfected in 1975, it raises the obvious question of why Lux 036 is doing a whole presentation on it in 2026.
Yes. The answer there is the relentless scale of modern technology. When engineers take Hadlock's elegant math and try to feed it a modern circuit netlist like the blueprint of a microchip containing millions of microscopic wires,
it crashes.
The algorithm hits a terrifying computational wall. The calculation just gets way too heavy.
Too heavy how?
Specifically, the bottleneck is calculating those all pairs shortest paths on the dual graph. The time it takes to compute that scales cubically. In computer science terminology, it has a time complexity of big O of V dual cubed.
Oof. Let's unpack what cubic scaling actually means for a processor, because it is brutal. It basically means if your network gets 10 times larger, the math doesn't take 10 times longer to solve. It takes 10 times 10 times 10.
It takes 1,000 times longer.
Exactly. So for a modern circuit netlist with thousands or even millions of faces, the processing time stretches from like seconds into literally months.
And that is the exact problem the 2026 presentation solves. The solution is an optimization called biconnected component decomposition, or BC decomposition. The researchers leveraged a hidden structural property of the Anx-Sekou problem on planar graphs, which is that the results are additive over biconnected components.
We probably need to define what a biconnected component looks like for everyone.
Sure. Imagine a sprawling network that has a structural bottleneck.
Yeah.
So 2 large, dense clusters of nodes that are connected to each other by only one single node in the very middle. That single critical connecting node is called an articulation point.
Right.
If you were to delete that one node, the entire graph would split into 2 completely disconnected pieces.
It's an hourglass shape, essentially. The articulation point is the pinch in the middle where the sand falls through.
Exactly. So a biconnected component is a solid block of the network that contains absolutely no articulation points inside it. You'd have to aggressively remove at least 2 or more nodes to break it apart.
Okay, so how does that help us?
The breakthrough insight here is all about cycles. Because these separate components only touch each other at that single articulation point, they can never ever share any edges. It is physically impossible for a cycle to loop through one block, cross the pinch point, travel through the second block, and somehow circle back without crossing that pinch point a second time.
And since MX, so ET is ultimately about breaking cycles to resolve those frustrated faces, the fact that no cycles overlap means the math in one block has absolutely zero impact on the math in the other blocks.
Exactly. You can completely sever the graph at those articulation points. You just hand each block to the processor to solve entirely independently, and then you union the final results together at the very end.
Okay, let me try an analogy here. It's like trying to perfectly divide a giant, really intricate, solid chocolate bar. If you try to snap the whole massive thing in half all at once, the force will probably shatter it into a chaotic mess.
Right, total disaster.
But if that chocolate bar has those deep grooves pressed into it, those are our articulation points. You don't try to snap the whole thing, you easily break it down along the grooves into bite sized squares. You divide those tiny squares effortlessly, and when you push the divided piles back together, you get the exact same perfectly split result, but you used a fraction of the energy.
That analogy perfectly captures the mechanics, yeah. By conceptually breaking the graph apart at the articulation points, we aren't changing the final maximum cut at all, but we are fundamentally altering the geometry of the processing time.
Let's actually talk about the math of that processing time because it's nuts. When you're dealing with a problem that scales cubically, breaking the input data down doesn't just save a little bit of time, it causes a massive collapse in computational weight.
It really does.
If you find just one articulation point right in the middle, splitting your network into two equal blocks, the math changes from n cubed to two calculations of half n cubed. That mathematically resolves to n cubed divided by 4.
You get an immediate 400% performance boost just for slicing the problem in half once. And obviously, the more components you break it into, the more extreme the speed up becomes.
So, how do they physically find those pinch points in the code?
Modern software utilizes Tarjan's bridge finding technique, which relies on a depth-first search. It's actually a really fascinating mechanism. The algorithm essentially drops a digital breadcrumb trail.
Like Hansel and Gretel.
Exactly. It relentlessly walks a path deep into the network until it gets stuck. If it explores a whole cluster of nodes and realizes the only possible way back to the start is to walk backward along the exact same path it just came down, it knows that connection is a bridge.
And the node connecting it is an articulation point.
Right, so it rapidly crawls the graph and collects these independent node sets.
But the speed up for the shortest paths calculation is only half the victory here, right? The decomposition also completely transforms how we handle step 5, the MWPM, where we calculate the perfect matching of the odd faces.
Yes, because the matching step is also fundamentally cubic in complexity. But because we've shattered the graph into these tiny bite-sized biconnected components, the number of frustrated odd faces trapped inside any single block drops dramatically.
Just structurally.
Exactly. The researchers documented that after applying BC decomposition, the vast majority of blocks end up containing 18 or fewer odd faces.
Okay, why is the number 18 so critical here?
Well, it comes down to that factorial explosion of combinations we mentioned earlier. If a block had, say, 100 odd faces, the number of possible ways to pair them up is so astronomically large that you'd have to use a greedy approximation.
And a greedy algorithm just looks at the data and says, what is the absolute cheapest pairing right next to me in this exact moment?
Right. It takes the immediate cheapest option. But that short-sighted decision might force a terribly expensive pairing later on. You lose precision. But 18 faces? That is a small enough combination space that a standard modern processor can hold the entire matrix in its memory at once.
It basically drops below the threshold where approximations are even necessary.
Precisely. So instead of a greedy guess, developers can deploy an exact dynamic programming approach.
Okay, dynamic programming.
Yeah, which maps out overlapping subproblems. It explores the combinations perfectly to find the absolute optimal overall setup rather than just taking what looks good in the moment.
Right.
The decomposition doesn't just make the algorithm exponentially faster, it ensures the MWPM step is mathematically perfect.
Speed and absolute precision. I mean, that's the holy grail of optimization right there. And the source material makes it clear that this isn't just a theoretical white paper either. They highlight actual code implementations built for production.
Yeah, they really brought this to life.
There is a Python package called netlistx that handles this BC optimized logic. And for raw industrial grade performance, they built Netlist X CPP in C++X.
And honestly, the C++ implementation is a masterclass in modern software engineering. It specifically leverages C++ 20 coroutines to perform what's called lazy iteration.
Let's translate lazy iteration for a sec. It essentially means the computer acts like a highly efficient procrastinator.
I love that. Yeah.
Instead of aggressively calculating and storing the entire massive map of data in its memory all at once, a coroutine pauses. It only calculates the exact piece of data the algorithm needs at the precise millisecond it's asked for it.
It's like a chef who refuses to chop all the vegetables in the morning, but waits until the very moment a customer orders a salad.
Exactly. It saves massive amounts of memory overhead.
And they also manage the build process using Xmake, which is a modern, incredibly fast build utility that replaces older systems like CMake. It just points to a highly streamlined, contemporary development pipeline.
Okay, this all sounds like absolute magic. I mean, we took a 1975 mathematical cheat code, dusted it off, supercharged it with biconnected component chunking, and ran it on ultramodern C++ coroutines.
It's quite the journey.
It is, but I have to play devil's advocate for a second. Is there a catch? Like, are there scenarios where a data scientist should look at their network and decide not to use this decomposition?
It's a vital question. Because, yeah, this optimization is wildly powerful, but it is highly dependent on the physical shape of your data. BC decomposition is a lifesaver for sparse circuit netlists, sprawling grid-like structures, or hierarchical designs.
Basically, things that look like chaotic spider webs with lots of natural pinch points.
The chocolate bars with lots of deep grooves.
Right.
But it offers absolutely zero benefit if your graph doesn't possess those pinch points. If you're analyzing a highly dense planar graph or a tightly woven triangulated mesh, it might be one giant, solid biconnected component.
Ah, so if you run the Targent search on that,
The algorithm will crawl the entire structure, realize there are no articulation points, and you will have wasted processing power only to end up right back at the original cubic bottleneck.
ouch.
Yeah. It's also completely unnecessary for very small networks, say under 50 nodes. At that scale, the administrative overhead of actually splitting the graph takes longer than just solving it outright. Knowledge is most powerful when you understand the boundaries of its application.
Use the right tool for the exact shape of the problem. Makes perfect sense. So, what does this all mean when we pull back and look at the big picture? We started with the famously intractable NP-hard problem, trying to cleanly divide a complex network while maximizing the tension across the gap.
Right.
We learned that if the network can be drawn flat on a piece of paper, a brilliant mathematician in 1975 found a workaround. By ignoring the nodes and looking exclusively at the empty spaces, the faces, he realized the odd shapes were mathematically frustrated.
And by running an algorithm to find the absolute cheapest way to remove that frustration, he threw away the mathematical minimum, ensuring he was left holding the absolute maximum.
And then we jumped to 2026 to see how engineers forced that elegant solution to survive the crushing scale of modern microchips.
Yeah.
By utilizing depth-first search to identify articulation points, we can fracture an impossibly heavy calculation into tiny, independent, lightning-fast blocks.
Switching to exact dynamic programming to get a flawless result in a fraction of the time.
If you're listening to this and facing an overwhelming, seemingly impossible project in your own life or career, I think the takeaway here is really profound. The answer isn't always to brute force the whole massive problem at once.
No, rarely is.
Look for the underlying geometry of your challenge. Are there natural articulation points? Can you find the pinch points where you can break a massive, intimidating undertaking into independent, manageable blocks that you can solve perfectly on their own?
It completely reframes how you approach complexity, doesn't it? You don't have to swallow the problem whole.
You really don't, and it leaves me with one final, lingering thought to explore today. Hadlock solved an impossible problem not with brute force, but with a total shift in perspective. He didn't look at the tangible objects, he didn't look at the nodes, and he didn't look at the connections. He found the perfect answer by deeply analyzing the empty space between them. So what other intractable problems in science, in business, or even in our own personal lives might suddenly become perfectly solvable if we just stopped staring so hard at the objects themselves and started analyzing the empty space?
That is a phenomenal question to ponder.
Something to mull over until next time.